This is the first mini lecture from section 3.1 of the textbook. You can find the slides that I'll be using on Blackboard. I would suggest printing them out and then copying down as I write the solutions. If you're not able to print them out, I would suggest simply pausing the video every so often and copying down the whole slide. Okay, so if you'll recall, toward the beginning of the semester, we put ourselves in the shoes of this prehistoric shepherd. We're trying to imagine how this shepherd could keep track of his sheep without being able to count. And the solution we came up to that problem was that he could use pebbles. He would just gather pebbles, and each pebble would represent one of the sheep, so that at the end of the day, he could check and make sure that the pebbles matched up with the sheep. And he could do this entirely without counting. Well, suppose instead of having just a basket of pebbles, which could be lost at any point, he wants a more permanent record of his sheep. Instead of having a basket of objects, he could basically write it down, just make a mark for each of the sheep that he has. So instead of using pebbles, he could use marks. So one solution would be to make tally marks on a stick or a bone. If we suppose that he has, let's say, 23 sheep, even though he doesn't know that because he can't count, he could just look at each sheep in turn and make a mark for each one of those sheep, just like he would put a pebble in a basket. So you've got the first sheep and the second and the third, and it just keeps going like that. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So, those marks then would represent his sheep. And archaeologists have actually found artifacts that are marked like that. It seems like probably prehistoric people were using this to keep track of things. Of course, it's pretty hard to read that. If you're going to try to use this to figure out whether you've lost sheep or not, or how many sheep you owe somebody, it's going to be difficult to decipher that. So one thing you could do to make it easier, which is what everybody does when they keep score at basketball games and things like that, is to group the tally marks into fives. So there you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And there you go. So this idea of grouping markings into markings that represent a larger amount, that's the basis behind all numeration systems. So when you look at this, what you see is 4 5s and 3 1s. You don't see the 23 immediately, and you don't just see a jumble of 1s. You see there's 1, 2, 3, 4 groups of 5, and then 3 1s. Okay, that idea is the idea behind every numeration system. Okay, in this section we're going to talk about 5 historical numeration systems. The first system we're going to talk about is the Egyptian system. So this is the system that was used in ancient Egypt. And like ours, it is based on powers of 10. Okay, so that makes it a little bit easier for us to understand. So the number 1 would be represented by a staff or just a little line. The number 10 is represented by what the book calls a yoke, like you use to yoke a pair of oxen, or an ox rather. 100 would be represented by a scroll. You can find these pictures in the textbook, by the way. 1,000 is represented by a lotus flower. The 10,000 is represented by a pointing finger. 100,000 is represented by a fish. with a smiley face. And a million is represented by what the book calls an amazed person. Okay, so these are the symbols that they used to represent their numbers. They had a different symbol for each power of 10, from 1 through a million. And it's pretty easy to use. You just write down as many symbols as you need for each power of 10. Okay, so let's work through one example. So let's write the numbers 227 and 145 in Egyptian notation and add them. So 227, we need 2 scrolls, and 2 yolks, and 7 staffs, then 145, we need 1 scroll, 4 yolks, 5 staffs. Okay, notice when you draw these numbers that the order of the symbols doesn't really matter. It's customary to have the larger ones on the left and the smaller ones on the right, but I could scramble the picture up and it would still represent the same number. Compare that with our system, where if I have this 2, 2, and 7, I can't just mix those digits up. Like I can't exchange the 2 and the 7 and expect that that's going to represent the same number. So while this is very similar in some ways to our system, it's also rather different in that respect. In this Egyptian system, the order doesn't really matter. There's no concept of position or place value. Okay, so step 1 in adding these, I'm just going to put the 2 sets of symbols together. I'm not really going to worry about what this represents yet. We're just going to lump it all together. Now we have 3 scrolls and 6 yolks, and then 7 plus 5, or 12 staffs. So that represents the answer, and there's nothing wrong with that exactly, but yet typically we would want to use as few symbols as possible. So instead of having 12 staffs, what I should really do is take 10 of those staffs and replace them with a yoke. Okay, so I make an exchange. This is similar to what we do when we make exchanges when we add in our own numeration system that we learned in grade school. Okay, so we still have our 3 scrolls. Now I have 6 yolks. I have 7 yolks. And I have 2 staffs left over. Okay, and what does that represent in our system? Well, it's easy enough to tell, but I don't have to worry about that. I added the whole thing completely in Egyptian notation. So think about that difference I just mentioned, about how, in the Egyptian system, you don't have to worry about the order. You kind of want them in a certain order, but it doesn't matter to the number. But in our system, you definitely do care about the order. That might seem like a good thing about the Egyptian system because there's less you have to worry about, but it's actually a huge drawback. So here's how it affects the system. In the Egyptian system, each new power of 10, like 10 million or 100 million or a billion or a trillion or a quadrillion or whatever, they all require new symbols. So if I'm, for some reason, I'm wanting to talk about 10 million or 100 million, I'm going to have to make up an entirely new picture, something past that amazed person. And I'm going to have to tell everyone what that picture means. And no one is going to understand what I'm talking about unless they know what that little picture means. And so that means it's kind of hard to talk about big numbers. You'd have to have some kind of centralized authority that could make sure everyone was on the same page. And so it's kind of inconvenient. Um, it might be useful for for practical purposes. You can talk about amounts up to a certain point, but if you wanted to do something like science with it, then it's got a lot of drawbacks. Okay, and the fact that you have to use a different picture for each new for each new power of 10 rather, is tied directly to the fact that it's not making use of place value. It's the fact that we can scramble up these little symbols and it still represents the same number is tied to the fact that each new power of 10 is going to require a new symbol. Okay, it's because it is not using place value, which our system does use.